Every engineer has written one. That single, isolated script that pulls an API every 5 minutes, checks a condition, and fires off a Slack message. It runs quietly on a server, holding your basic integrations together, until it silently fails at 2 a.m. and nobody notices until Monday morning. To solve this, we can replace brittle manual code with n8n. It is a self-hosted workflow automation platform that lets you build and monitor integrations using a visual, node-based editor instead of scattered text files. Today, we are going to spin up our own n8n instance using Docker to guarantee our data stays private. Then, we will build an automated pipeline from scratch that fetches open GitHub issues daily and routes a summary directly to a Slack channel. Transitioning from hidden scripts to a node-based graph makes failures visible. If a step fails, you don't have to dig through server logs to find the error. The graph shows you exactly which node stopped the data flow. This conceptual architecture map shows how we handle data security. By running n8n locally and connecting it directly to an on-premise Postgres database, the system remains blocked off from external internet traffic. To initialize this environment, we execute a single Docker run command, mapping to port 5678. In 3 minutes, the container spins up, granting immediate localhost browser access to the editor. Inside that editor, workflows operate as a directed acyclic graph, or DAG. Data flows continuously in one direction, meaning every automated sequence relies on a singular initiating event. Instead of writing a hidden server cron tab file, we drag a visual schedule trigger onto the canvas and configure it to run at exactly 9 a.m. daily. By containing the infrastructure within a self-hosted Docker instance and replacing server tasks with visual triggers, you maintain direct control over the execution environment and see exactly when and where the automation begins. Step 1 is pulling outside information into our secure graph. For our alert pipeline, we need to query the GitHub API to find the exact number of open issues in our repository. This schematic demonstrates the centralized credentials vault. Instead of hard-coding API keys directly into your configuration files, you store them securely in this central vault. The system then routes temporary access tokens to individual workflow nodes on demand. We place an HTTP request node on the canvas and set the method to GET. Because we configured our credentials in the vault, we select them from a dropdown to securely authenticate the query. Network timeouts happen. To protect the system, we establish an automated retry policy in the node settings, instructing the workflow to pause and try again if the initial request fails. Separating authentication from the execution logic and applying automated retry rules addresses 2 common failure points in traditional scripting: credential leaks and brittle network dependencies. This pipeline visualization shows the item-centric data model. When the API returns an array of open issues, the workflow splits that raw JSON into distinct modular items, processing them simultaneously. We pass these items into a code node. Here, we write a few lines of JavaScript, stripping away the raw JSON structure to extract just the issue numbers and titles into a consolidated text summary. Next, we add a Slack node to finalize the payload. We use bracketed expressions to dynamically insert the transformed text and issue count from our code node directly into the message body. As a final safety net, we create a secondary workflow beginning with an error trigger node. If any part of our main pipeline fails completely, this trigger activates and routes an immediate failure log to a dedicated engineering channel. Treating data as standardized items flowing through strict visual gates turns complex manipulation from a tedious coding task into a transparent pipeline with built-in fault tolerance. At 9 a.m., the schedule trigger fires, and the automated bot delivers a clean, formatted summary of all open GitHub issues directly to our engineering channel. In 4 distinct nodes, we replaced a scattered, fragile script with a cohesive system running on our own infrastructure. Because this architecture is completely modular, scaling it is straightforward. You can swap a basic API for a large language model, using this same framework to orchestrate multi-step AI agents. Mastering visual orchestration doesn't stop external APIs from going down, but it does ensure those failures are caught and handled automatically. This structured approach is the necessary foundation for moving from simple alerts to deploying intelligent, multi-step agents.